I'm Ozgun from Citus Data. Prior to Citus, I was in the distributed systems engineering team at Amazon, which over the years more or less morphed into AWS. And at Citus Data, we make PostgreSQL scale. That is, we shard and replicate your PostgreSQL tables. When you send a query to your PostgreSQL cluster, which is sharded across many machines, we take that query, we parallelize that query, run it across many machines, merge the results, and give them back to you. So that's what we do at Citus. We make PostgreSQL scale. And the title is fairly long. I'm going to talk about a new PostgreSQL feature today, a relatively new PostgreSQL feature. And in fact, I'm going to talk about two things. One is, why do SQL databases have a bad reputation for scaling out? And what new PostgreSQL feature is about to change that? That's my talk. I have 8 slides. It's a fairly technical talk, so if you have any questions during the talk, please feel free to interrupt me. And here we go. My introductory slide is SQL databases are known as hard to scale. Why? And in here, I'm going to cover 3 reasons. And then I'm going to jump into another reason in the next slide. These are, unfortunately, there is no simple or single answer about this reputation, as in like, why are they hard to scale? And even a summary that's in here is an oversimplification. The 3 reasons, as I see them, are like, 1, scaling and fault tolerance is hard, period. Like, as a technical problem, scaling is hard. Anybody who's worked with distributed systems will know that one of the challenges, let's say you have your databases, you have your shard, and now you're replicating your shard. Now the problem is you're modifying state, you send a request to this guy, and you need to keep the replica consistent with that guy in the face of node failures, network failures, and that's just hard. Another alternative is you can have them diverge from each other, but when you present that state to your end user, you need to reconcile that state and show them a consistent view of the data. That's on writes. On reads, instead of having a single machine, now you're going over the network. You have the network bottleneck. You may need to shuffle a lot of data across that network, and then your network is going to become a bottleneck at that stage. So technically, it's a hard problem to solve. That's number 1. Number 2 is SQL means a lot of different things to a lot of different people. It's a spec that evolved over the past 30 years, and it's more or less anything and everything you can do with your data. So when somebody talks about SQL, they mean different things. It may mean cross-machine transactions, like you're a financial institution, and you're withdrawing money from my account, and then you're debiting it to someone else's account. And then those 2 accounts live on different machines. And you want to do this in a single transactional block. Or instead, you want to do lots of short inserts and updates and reads, and you want to do these at high volumes. This is where the NoSQL guys come into the play. Or even differently, you have complex data warehousing needs. So you have lots of select queries, you're doing ETL, you're doing all of this other stuff. And all of these challenges are different challenges. Like a transactional challenge across different machines is different than high insert and update ratios, which is different than complex data warehousing workloads. So that's another reason when people think of SQL, they think of this like huge thing, where in fact it's different use cases. And the 3rd reason is, there are scalable SQL solutions out there. Like, say there is a Teradata, there is a Vertica, they're out there, but then those are typically millions of dollars contracts. When you think of scalable SQL, you're more thinking of it in a tech space. Like, you're a technology company, you want to have the solution, you don't want to pay $10 million to an enterprise scalable SQL solution out there. You're more looking for your open source alternatives. So these are 3 of the reasons why SQL databases have the reputation that they have today, more like both on the technical part and also on the business part. And another reason is, as a language, SQL, part of that reputation is also the language itself. SQL is a declarative language. It's text. And let's take a step back and think of it this way. You have your MySQL database. You have your PostgreSQL database. It does your transactions just fine. It does your storage fine. It has indexes, all this feature set. And now you want to build the distributed functionality into your database, the scaling out of functionality into your database. I have a simple example, and I'm going to walk over this example in the next couple of slides. Let's say you declare your table. This is customer reviews. Think of it as Amazon presenting customer reviews to their users. And I have multiple columns in here, but I just picked 4 of them. So this would have been your typical table declaration, and then you probably have multiple indexes on it. And now you want to build into the database this functionality for, you want to shard this database across many machines. So you want to build that functionality. So you pick a sharding dimension, and you want to pick a partitioning or a sharding method on top of it. How do you build this into the database? Obviously, one way is you take the database, you start forking it. Another way is you do this at the application level. But the question is, how can the underlying framework provide this to you while still giving you the MySQL or the PostgreSQL experience? And here I'm diving, now that we declared our table and assume we wrote that functionality for sharding out your database and your SQL schema, then you want to start throwing your queries into it. These are insert queries or these are update queries. Now the thing that the database needs to do, or your scaling database needs to do at this stage is, they need to, like let's say you have the insert into, the database needs to take this SQL query, it needs to parse it, it needs to run semantic analysis on top of it to say, okay, this text query that's coming into my database corresponds to a database table, which is customer or multiple database tables. It has these fields, these columns in it. I need to check that the data types match. I need to check that the constraints match. And only after the database has done all of these things, you need to take that query and you need to say, okay, the last column in here corresponds to the thing that I'm going to shard this thing on. Or whereas in here, these columns, these filters are the things that I need to apply on my database in order to shard this properly. And the question becomes, how can you do this in MySQL itself? How can you do this in PostgreSQL itself? Because it's not easy. It's almost you want the database to do all of these things and then somehow build the functionality into the database without really forking it out. Any questions up until this point? Does this make sense? So that's more or less the challenge. And let's not even talk about select queries. So the previous example was at least you're writing into your database, you have this insert, but then if you have a select query, if you want to analyze your data, if you want to do data warehousing, real-time analytics, the query that you're going to look at is going to be something very complex. You need to really have the database's cooperation to be able to answer this query. Not even distributed to understand what it means. The thing has user-defined functions, aggregate functions. This one doesn't have complex joins, but it may have complex join operations, subselects, window functions. And without really duplicating all of that code, it's really hard to understand what this query even means so that you can start thinking about how do I scale this thing out? How do I do this efficiently over the network? This all comes down to, given what you've seen, we looked at a table schema and then we said, okay, this is how we can actually partition, shard this data, replicate it, and then we've seen the inserts and the select. How do people scale their SQL databases today? It's typically 1, 2, 3, 4, and when we go and talk to people, we see 1 and 3 is more common than 2, and I'll explain why that is in a sec. The first one is you shard and replicate. You push all of that logic to the application level. That's actually what the NoSQL databases do, because SQL as a language doesn't have the concept of a partitioning column. If you look at a NoSQL database, NoSQL databases have keys and values, and that's very simple. Like the key is what you partition on. So NoSQL databases push all of that complexity to the application level, and then you as the application writer have that contract. And you can also do the same thing if you're using a SQL database. You push all of that logic at the application level. You know how your database is sharded, and you know how you need to route your requests, replicate your data, and you get to decide how you handle failures. So that's like number one. Our second version is you use middleware. These are typically stripped down versions of databases. A stripped down version of MySQL, a stripped down version of PostgreSQL, which has some of the logic that it needs for routing these requests, but not all. So it's simple. We see this less frequently than number one, just because understanding somebody else's middleware and tailoring it to your needs is almost as much work as the number one option. And number one is a lot of work. It's typically the bigger companies that do this. So people prefer to go with number one just because it's number two is neither here or there. And number three is you take PostgreSQL, you already know you need the parsing logic, the semantic analysis logic, all of that, and you fork it. And once you fork it, you never look back. In fact, there are maybe a dozen databases out there that are commercial forks of Postgres that took Postgres and then they went in one direction, and they're still on Postgres version 8.1, 8.2, because once you fork it, it becomes very hard to integrate back. And in fact, if you look into PGSQL hackers list for these commercial forks, a good number of these commercial forks also propose patches. They've been proposing patches saying, hey, we made PostgreSQL scale for this data warehousing workload, why don't you take our patch? And the PostgreSQL guys say, no, we're not taking your patch because that patch breaks this transactional logic. We're not taking that patch because that patch breaks the data warehousing logic. And at some point, the Postgres guys said, okay, we're building a reliable database. Can you make PostgreSQL a platform? Something not only that's reliable, very solid with all these features, but something that's more that people can take, build their own logic on top of it, that they can extend, hack their own functionality. And this is, as of version 9.1, what they came up with. This is the PostgreSQL extension framework, and then the PostgreSQL hooks, more or less. What they've done is, they took everything in the database and they made them into APIs, into contracts. If you open a relatively new PostgreSQL documentation, you're going to see there's a chapter devoted to extending SQL. So you can write your own aggregate functions. You can write your own user-defined functions, your own operators, your own indexes, your own storage engines. More or less anything that you want to write in PostgreSQL, you can do this. In fact, there are over 150 PostgreSQL extensions out there today, ranging anywhere from Bulgarian social security ID validation as a data type to count distinct approximation for very fast, these are the distinct number of, say, customers that you have, diverse set of functionality, columnar stores, semi-structured data types, JSON, HStore, the semi-structured, so this is all there. And then this is really powerful, and only part of it. The second part is they took a step forward and then they said, okay, you have the APIs to your aggregate functions, but what if you could intercept any hook within PostgreSQL itself? This is the contract that we defined for you, so you can augment, do your own thing, do a completely different thing at the parsing level, at the planner level, at the executor level, at the utility level. We're going to provide you these contracts. And now with these contracts, you can hook into PostgreSQL as a shared object, get them, and then do whatever you want to do as long as you go by the contracts. These are very tough contracts to follow, by the way. They take a long time to understand, months as in understanding exactly how you need to follow by. But once you get them, everything becomes incredibly simple and very powerful. The previous insert logic that I mentioned, it just becomes you grab the planner hook. At that point in time, the query has already been parsed, has already been validated, has already been transformed into a form that's really easy to understand. And all you need to do is just say, get me the partition columns value, and I want to hash it. And then this is the shard that it maps to. Like very, once you understand that, and then that's at the planner level. So you grab the planner hook and you do that. And for someone who's been working on databases, and modifying databases for a while, who doesn't like forking databases, because once you fork the database, you lose that. This is extremely powerful. I think it will take people a while to figure out these contracts, to understand and to learn the contracts, but once they do, like the community is already moving in that direction, is going to move in this direction, and we think this is the best way to just make SQL databases scale. They are without forking, without doing it at the application level. The entire thing on that idea, on these PostgreSQL new APIs. We're Citus Data, we make PostgreSQL scale. And if you have any questions, I'd be more than happy to answer them.